I'm your man. This guy. J to the O to the N, Wilson. And today, we're starting Module 6. We're going to do Lesson 6.1 and 6.2. We will identify and represent functions from tables, mapping diagrams, and graphs. And then once we're done with that, we're going to learn how to describe functions, graph functions, and determine whether or not a function is linear. So, what exactly is a function? Now, functional relationship or expression always involves one or more variables. Now, the value put into the function, we should know what this is. What goes into the function is known as the, that's part of it, it's known as the input, which is also the x value. And then what comes out the other side of the function is known as the output. That sounds familiar. We've heard that before when we dealt with equations. Something goes in, something comes out. In functions, it's even more specific. Specifically, for something to be a function, I don't know if you want to underline this, you want to put a little star next to it or something, but for it to be a function, each input is paired with only one output. That means if I put 1 into the function machine, I will always get out the same number depending on the function itself. We'll talk about that as we go through functions. But each input is paired with only one output. This definition is about as important as it gets for this class, your state test, my test, everything else. Trust me, you will see this multiple times. Multiple times. Did I say multiple times? I did. Anyway, I want you to think of a function as a vending machine. So think of you. You go up to a vending machine. You look at it. You see something delicious. You decide you'd like to purchase it. So what do you do then?
Press E3.
Not yet. There you go. You put something in. You put in the dollar. And then that would be your input. Then what do you do after you press the dollar?
Press E3.
Press E3. That is technically your function rule. Depending on what you press, is that going to change what comes out? Yes, it is. So input your dollar. Your function rule would be whatever button you press, and then your output. Maybe you get a Coke. Maybe you get some taquitos. Maybe your stuff gets stuck and you freak out and lose your mind. Go, oh, my dollar back! That happens in the real world. When we're dealing with function rules, we put something in, we always get something back out the other side. So, input, function rule, output. To show you how this works, we're going to pick a couple inputs. I'll pick a negative one. I'll pick a negative input, something like -2. And then I'll pick a 0, because I like to see what happens if I put 0 in there. And I'll try a positive output. Give me a positive number between 1 and 9. 2, somebody said 2, all right, so there we go. -2, 0, and 2. So those are my inputs. Usually your inputs will be predetermined for you. If you are ever asked to select your own inputs, make sure you take a look at the situation. If we're talking about real world, we're talking about like you going to work and earning money. Let's say the function, let's say this represented how much money you make. You wouldn't work -6 hours, would you? No, you could work 1 hour, 2 hour, 3 hour, 4 hour, depends. So make sure if you are ever asked to select your own inputs, look at the situation, select inputs that are appropriate for the situation. Okay. So, we have our inputs. Now we're going to take these, we put these into the machine, which basically means that this number, -2, is going to replace what here?
X.
The x. So this becomes 3 times -2 plus 7. What is 3 times -2? -6, and then Liana, what is -6 plus 7?
It's 13.
-6 plus 7.
Oh, -7. 1.
-6 plus 7 is 1. So I put in -2, I got out a 1. This is an x, and this is a y, which means that using those two numbers, I can create what? A coordinate pair. So the coordinate pair for this input and output would be -2, 1. Because as I'm sure you guessed, we can also graph functions. Right now, we're just starting with the basics. We have an input, we have a rule, we have an output, we create a coordinate pair. Pretty simple concept. Let's try 0 here. So we take 0, we put it into the machine. 3 times 0 plus 7. What's 3 times 0?
0.
0. 0 plus 7 is?
7.
7. So input is 0, output is 7, 0, 7. That makes sense. It does, because I want you to think about this if this was written, this rule, technically it's written in slope-intercept form, right?
Yes.
Looking at that, what's the y-intercept? 7. You're right, it is. It's 7. 0, 7. That makes sense. We'll try the last one here. We put in a 2. That's going to give me 3 times 2 plus 7. What's 3 times 2?
6.
6 plus 7 makes 13. So we put in 2, we get out 13. Inputs, output, coordinate pairs, pretty simple process. You're simply taking an input, you substitute it in for the x, you get an output, that becomes a coordinate pair. That's basically what a function does. Now this is a very simple function, very simple. You have a variable, you have a constant, there's no exponents, nothing crazy. Of course, as you imagine, they do get a little more crazy from there. But it still just boils down to order of operations. Input goes into the machine, out comes the output, and that becomes a coordinate pair. And then once I have coordinate pairs, could I graph this function, yes or no?
Yes.
Yes, I could. And really, to graph it, I only need how many inputs? No, I need 2 inputs to give me 2 outputs, to give me 2 points. Now, I'd like to use more than that because depending on the graph, sometimes just using 2 inputs and getting 2 outputs may not give me a real clear picture of the graph. But really, to graph any line, I really just need 2 points. All right, so looking at this function, once again, think of it as y equals mx plus b. We already know what the y-intercept was. That was, it's not there for some reason, that's 7. What's the slope of this function? 3. It's right there. It's next to the x, just like in slope-intercept form. There's a lot of carryover here. The only real difference between this and slope-intercept form is that we replace the y with this. The y is gone. It's replaced with f of x because the f stands for functions. A function of x because we're replacing the x in these problems. Okay, so that's what a function looks like. Now, here, we're given the rule. But what if I was not given the function rule? And I was asked to go in and I was asked to write the function. The good thing is you already know how to do this because it's the same process as when we were writing equations in slope-intercept form. You're given a table of values, right? Input, output, that's x, that's y. So to write a function, same thing to write an equation, we need to find the slope and we need to find the y-intercept, initial value, the b, whatever you want to call it. So a function can be represented in various ways. Some of the most common are mapping diagrams. We're going to talk about those in a second. Tables, graphs, and ordered pairs. But before we move on to that, I want to make sure that you guys understand how to write a function rule. Same exact process as writing an equation in slope-intercept form. This is something we all know how to do. Quick refresher, this is the only time you're going to see this in here. After this, I expect you to know how to write the rule. Then we'll move into all the different ways we can identify functions. So everything else here, we know how to do. We want to write a function for this. We have coordinate pairs, 247, 149, 180. We need to find the slope. So let's go to Julio. I want to find the slope of this function table. We've done this many times. X, Y, X, Y, X, Y. Pick 2 coordinate pairs. 2 and 40. Okay.
And 7 and 140.
7 and 140. Okay, then this would go into your slope formula. So, tell me, what are you writing?
140 minus 40.
140 minus 40. Do you know how to do this? Feel free to work ahead. What goes in the bottom?
7 minus 2.
7 minus 2. Just make sure that your work matches ours. 140 minus 40 is 100. 7 minus 2 is 5. So that means that my slope here is going to be 20. Once I know that, I know the slope, I must still go and I must find the y-intercept. So to do that, remember this equation? Y equals mx plus b.
Yep.
We know the m, and we know a whole bunch of xy's. What, Kian, what y-axis do you want, what xy coordinate pair do you want to use to find the b?
2 and 40.
2 and 40. So we're going to use 2 and 40. And we will substitute in. Tell me, what am I writing, Kian, when I substitute in? There's your y, there's your x, there's your y, there's your m. Tell me, what goes in?
Y equals,
Well, the y, which one of these is the y? The 2, the 40, or the 20? Remember, x, comma, y, and that's my m. So substitute in. Tell me, what am I writing into this equation to solve for b?
2.
No, which one of these is the y value?
Oh, 40.
40. 40 is equal to
20.
20.
Oh, x plus
No, we know the x. What's the x?
2.
2. 20 times 2 plus b. That gives me 40 equals 40 plus b. I think we all know what's going to happen to these 40s. What's going to happen to them?
Subtract.
They're going to cancel out. 40 minus 40. So that means my b here is 0. So my function here, f of x, we don't write the y this time. It's the same process, but instead of writing y equals, we write f of x is equal to 20 what? X. There is no y-intercept. So it's the same process. You've done this before. Writing a function rule is the exact same thing as writing an equation in slope-intercept form. I always show this to kids when we start functions to let you know that the hard math in this whole module, this part, is something you already know how to do. Everything else is just visual. This is about as hard as the math gets in this module. Okay, so we got one. Mr. Francois. We want to write a rule for this one. So, give me two coordinate pairs. 0, 10. Okay. 3 and 25. And what is going into your formula? 25 minus 10 over 3 minus 0. That gives me 15 over 3. So my m is equal to 5. Now, I want you to take a close look at this table. Do they give me the y-intercept, yes or no?
Yeah.
Yes, they do. The value of y when x is equal to 0. So if you want to go to the whole y equals mx plus b thing, you can, but it's already given me the y-intercept right here. If I have x at 0, whatever the number in the y position, that is my y-intercept. So my y-intercept is equal to 10. Right there on the table. Saves me some time. So for this one, I can write the function rule. Manuel, what is going to be the function rule here?
Fx equals 5x plus 10.
Perfect. F of x is equal to 5x plus 10. That's about as hard as the math gets here. Everything else is visual and just trying to understand the concept of what a function is. What's up?
So what's the function for the first one?
F of x is equal to 20x. There was no y-intercept. The y-intercept was 0 because this is a proportional function. We could say a proportional relationship, proportional equation. When we're in functions, it's a proportional function. So far it looks the same, but after the whiteboard you can see there is a difference between functions and equations. Any questions on what we did so far? No, because you're all going to have to write a rule in a second. All right, so 4 3 2 1. Okay, so let's talk about identifying and representing functions. The diagrams below these bad boys are known as mapping diagrams. On the left, you have your inputs. That's your x values. And on the right, you have your outputs. Those are your y values. For a mapping diagram to represent a function, these are mapping diagrams, by the way. For a mapping diagram to represent a function, each input, I told you you're going to hear this again, can only be paired with how many outputs?
2.
1 output. It's always 1 output. Each input can only be paired with 1 output. An easy trick to remember to identify if mapping diagrams are functions, an easy trick is to remember that each input, can only have 1 line coming from it. If there's only 1 line coming from that input, it means it's only paired with 1 output. So if you look here at this first diagram, look at the first input. How many lines are coming out of that input? 1. How many lines are coming out of the second input? How many lines are coming out of the third input? 1. So this would be a function. This input paired with only 1 output. This input is paired with only 1 output. This input is paired with only 1 output. So this mapping diagram does represent a function. Now, this part right here is not required at this grade level, but I like you to know it so when you get to the next grade level, you know what they're talking about when you see it. All the inputs, all the x values are also known as the domain. And all the outputs, all the y values are known as the range. Home on the range.
Remember range, Mr. Wilson?
Okay, so this is a function. 1 line, 1 line, 1 line. You have to remember this. It's very simple. Now, if we look at the second mapping diagram here, we look at the first input. How many lines are coming from it? 1. So that's good. We look at the second input. How many lines are coming from it? 2. That means that this input, is it paired with 1 output? No, it's paired with 2 outputs. And if it's paired with more than 1 output, that means it is not. a function. This does not represent a function. So as long as there's only one line coming out of all these inputs into all those outputs, you're good. But here, as soon as you saw those two lines coming out, that means boom! It's not a function, baby. It ain't a function. All right, let's try some of these together. Lickety-split-tastic. Let's go to lickety-split-tastic. All right, let's go to hand up. Boom. Is it a function? Yes, it is a function. Why? Because each input is paired with only one output. Boom. Function. Each input paired with only one output. You don't have to write this whole thing here if you don't want to. You can just write function. Your notes tell you why it's a function, okay? Okay, it's up to you. Whoa. Just jump it out of my pocket. Liana Zamis. Second one. Is that a function?
Yes.
Yes, it is indeed a function. Keep in mind, we don't care about the outputs. You're not looking at this. You're not. You're only looking at these. That's all we care about. How many lines are coming out of this input? How many? How many? One. It doesn't matter if the inputs are all paired with the same output. All that we care about is that each input is only paired with one output. One output, one output, one output. I'm not going to show you 6 of the same thing. I want to make sure you understand this concept, baby. Oh! Function. Each input paired with only one output. Now, did I give you a second? Okay. Ken!
Yeah.
You can answer this or you can have Peel answer this for me. Ken, is it a function?
Yes.
Okay. Definition
Oh
of
no
function.
no! Oh no no! I didn't see that. I didn't see that. That.
Okay, why is it not a function?
Because one has 2 lines going.
Because one has 2 lines, that means that this input is paired with more than one output. That's a no-no. That is not a function,
I meant
baby.
for that, but
That's not a function. He woke up. He got it just in time. All right, Lexi. Is that a function? No, because the input, the only input, 4, is paired with multiple outputs. That's no, baby. Can't have it. Wrong. Wrong. No. No means no. Or in this case, yet. Okay. Jason Francois. Jason. Jason. Is that a function? Yes, because each input, one line, one line, one line. Each input is paired with how many outputs? Just one output. Doesn't matter if it's the same output, kiddos. That is, in fact, a function. Okay. And Sergio, is this a function?
Yeah.
Yes.
Yeah.
What?
Because every output.
No, say it correctly.
Input
Each input is paired with only one output. Now that's correct, that is a function. Now let me ask you a question before we move on here.
That's 11.
If I were to look at this one, could I add one line to this to make it not a function? Yes. Does it matter which input I add it to? No, I can add it to this one, or this one. All of those would make this not a function because you have an input paired with more than one output. And that's a no-no, baby. Any questions? That's mapping diagrams. Let's move on. 4, 3, 2, 1. Alright, so now we're going to figure out how to identify functions from a table. Okay, so to determine if the table of values represents a function, we must, just like always, examine the inputs. We don't really care about the outputs so much as we care about the inputs. If an input repeats, and I want you to read this carefully, because I go a little deeper than the book does. If an input repeats and is paired with a different output, it's not a function. Now, in a table, the first thing we always look for is to see if an input, an x value, repeats. If it does, that's a big red flag that it may not be a function. But once you identify repeating inputs, you always have to check the output. Is it matched up with the exact same output? Because if it is, that's fine. If it's matched up with different outputs, that is not a function. So we're going to look at this first table. We look at all the inputs. It's very simple. Pretend these don't even exist. Look at the inputs. Do any of these inputs repeat? Yes or no? No. Then you don't have to do anything else. None of them repeat. That is a function. It does represent a function. It's just that simple. Look at my inputs. None of them repeat. Boom. That's a function. It's just that simple. Input 5, 10, 15, 20, 25. None of them repeat. That's a function. How do I know? Because each of these inputs is only paired with one output. Told you you'd hear it a lot. Now we look at this one. Once again, you ignore this. Just look at the inputs. Do any of these inputs repeat? Yes or no? Yes. Which one? One. This repeats. So once you realize that an input's repeating, you have to look at the outputs. Is this input paired with different outputs? Yes. Which means that it's not paired with only one output, it's paired with multiple outputs. So this does not represent a function. It's just that simple. You look at the inputs. It repeats. It's paired with 4, it's paired with 10. That doesn't work because if this was a mapping diagram, it would look like this. 1, 4, 10. And as we know, that is not a function. What's up?
So what if say 110 is paired, and then what if there's another 110?
If this was 110, is that a function, yes or no? Yes, because although the inputs repeat, it's paired with the exact same output, right? So if you were to write this as a mapping diagram, let's look. Let's see what it would look like. 1 and 10. That's a 10, by the way, horribly drawn. So that would be a function. Inputs can repeat if they're paired with the same output. But in this table, the input repeated, it was paired with a different output, and if you always want to double check it, make it a mapping diagram. Okay, I have 1. I don't have to write the 1 more than once, and it's paired with 4 and 10. So I have 2 different lines coming from this input to this output. That is not a function. It's not. Right. Okay. All right, let's try a couple of these. So again, questions on this so far? Pretty simple. Look at the inputs. Is it paired with different outputs? All right, let's go to my main homie, Adrian Nico. Is it a function? Yes or no?
Yes.
Yes. Look at the inputs. None of these repeat. There's nothing else I have to do. This is a function. Inputs do not repeat. Make sure you're writing this down. At the very least, write a function. If you want to write inputs do not repeat, that might be a good little thing to jog your memory when you come back around. Zozo! Is this a function?
No.
It's not. Why? What input repeats? 8. 8 repeats. And then the question is, okay, well it repeats, okay. Is it paired with different outputs? Yes, it is. If you were to write this as a mapping diagram, you would write 8, you would write 21, 34, and as you can see, that is not a function. Not a function. So this would be, let me erase all this here. Not a function. Inputs, repeatify. That's a real word made up by me. All right, Katrine. Is that a function, yes or no?
Yes.
Yes, it is a function. We look at the inputs. Do we care that these outputs repeat?
No.
No, we don't care. We don't look at the outputs. The only time we look at the outputs is if we see repeating inputs. These inputs, boom, 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 do not repeat. That's a function, baby. All day, every day. All right, all right. Boom, boom. It's made easy because by now the hardest part of this module is just finding the slope and the y-intercept. As long as you got that, functions aren't hard. If you still don't have that, you need to come see me for some help to practice it because that right there, knowing how to find the slope and the y-intercept and write that equation, also writing a function, that right there can make the difference between you passing or failing the FSA. Just that one part because of how much you see it over and over and over and over again on your FSA. Writing equations from tables, from graphs, from situations, writing functions, all the same thing. It makes up like 40% of your FSA. That makes, right there, just knowing that, you can almost guarantee yourself, if you know it front to back, you can guarantee yourself a pass on the FSA. Just that one thing front to back. No, I'm talking about knowing how to find slope, y-intercept, write an equation, function. There's so much wrapped around that. That's pretty much, that's it. I mean, you want to know the other stuff for sure. Well, like I said, especially for those of you like a 3. No, I don't get 3s. It's for peasants. I get a 5. Anything other than a 5, my parents would have told me I could see backyard.
Oh my god.
Alright, okay, so now we're going to identify functions from graphs. So we started off with mapping diagrams, then we moved to tables. But we realized that tables are just x and y values. We can take all those coordinates and we can throw them on a graph. The good thing about a graph, graphs are actually probably the easiest way to determine whether or not it's a function. Once again, to identify whether or not it's a function, you must remember inputs are the x values, outputs are the y values. Always remember that. For a graph to represent a function, none of the input values can repeat. None of them can repeat. If an input repeats on a graph, it means that the x value is paired with more than one output, or y value. That, as we know by now, is a no-no. That would make it not a function. Using that reasoning, does this graph right here, what do you think, kids? Does it represent a function, yes or no? No, it does not. Why? Tell me why.
Because on 2 and 9, it has two, I don't know.
It has two dots. So if we think of this as an input, 2, that means that this input right here is paired with two different outputs, 70 and 85. That's a no-no. If we look at 9, that's the input. The output would be 90 and 95. Can we have that for it to be a function? No, we cannot. You can also do something called, you might want to write this in, you're going to see it again in a second. It's called the vertical, write this in, line test. Here's what you do. Write that in, I'll tell you what the vertical line test is. It's pretty simple. Here's the vertical line test. You can take a pencil, and I'll take your pencil. Take a pencil, hold it vertical, which means straight up and down, right? And then, as you go up, do you go through more than one point, yes or no? Yes, you go through how many points?
2.
2, which means it would fail the vertical line test. If you draw a vertical line through this graph and it goes through more than one dot, remember, vertical is straight up, not diagonal, not horizontal, diagonal, straight up and down. If it goes through more than one point, that means that it fails the vertical line test, and if it fails the vertical line test, it is not a function. So it fails it here, and it fails it here. So it means this is not a function. And no, the input values 2 and 9 are paired with multiple outputs. And we also talked about 9. So this is not a function. There's multiple ways to see this. If you have 2 dots over any x value, that's a no-no. If it fails the vertical line test, that's a no-no. And this is more important when we talk about like a line that is actually graphed, as we're going to see in a second. Write this in and we'll move on. Like I said, this is not a lot of hard math stuff here. This is a lot of theory and memorization. You must memorize a lot of facts, and you must know the different ways that a function can be a function or not be a function. Okay. So, looking at this one. Is this a function, yes or no? No. Why not? Where does it fail? Fails the vertical line test at 71. Anywhere else?
70.
And 70. It fails here. It fails here. If you draw a vertical line, 2 points. 2 points. I don't even need to fail it twice. If it fails once, this would be not a function. The inputs 70 and 71 repeat. And in case you forgot about the vertical line test, I wrote it here again for you. I even wrote important on it because it is important. It's the easiest way to see if a graph fails as a function. So, I have a line that's been graphed. It is. But now, if you draw a vertical line through it anywhere on the graph, if it passes through more than once, it fails. So I draw a vertical line here. Does it fail? Yes, because it hits it here and here. It doesn't mean, and I want to point this out to you, if I were to draw something like this, is that going to be a function?
No.
No. Although it passes the vertical line test here, remember, if it fails anywhere along the line of a graph, it's not a function. So it passes here, it would pass here, it would pass here. But would it pass here? No. Fails, fails, fails. That is not a function. What about that? Is that a function?
Yes.
Yes, it is, because it doesn't matter where you do a vertical line. Passes, 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 passes the vertical line test. What about a circle? No, obviously not. Fails, fails, fails. What about, here's my favorite, a vertical line. Is that a function?
No.
No, because if you draw a vertical line, look, it fails infinitely, an infinite number of times. Fails, 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 fails to infinity. It fails from negative to positive infinity. That is literally the worst line to choose ever. What about this one? Is that a function?
Yeah.
Yes, because it passes, 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 passes from infinity to infinity. Yes. Boom. Okay. Down to the bottom of the page. La página and the bottom. Okay. So, we want to see if these coordinate pairs represent a functionification. Now, keep in mind, these are coordinate pairs. Input, output, input, output, input, output. Okay. Input, output, input, output, input, output, input, output. So the way to identify it, it's the same thing as a table, it's just written as coordinate pairs. Look at all of the inputs. Do these inputs repeat, yes or no?
Yes.
Yes. In fact, they're all repeating all the way across. Are they paired with different outputs? Yes. So this is not a function. I know, some of you already did. This is not a function. So if you look at the next one here, let's go to the Ticketland man. Azanza. Is that a function, yes or no?
Yes.
Yes. Although the input 4 repeats, is it paired with the same output?
Yes.
Yes, it is. It's paired with 5, it's paired with 5. Boom shakalaka.
Yes.
Yes, it is a function. None of the inputs repeat. 4, 6, 9, 5. That is as clear as it gets. All right, the last one, Camila Pinto. Camila, is that a function, kiddo? Yes or no? This one.
Yes.
Yes. Doesn't matter if all the outputs repeat. We don't care about the outputs. We only care about the inputs. 4, 5, 6, 7. No inputs repeat. Okay. Any questions? Any questions? All right. Well, today's go. Let's figure out what the difference is between linear and nonlinear functions. This is the same application as what we did with equations. Once again, remember that with equations and functions is kind of the same thing. I wrote these with y so you can see the similarities here. We're looking for a couple things. 1, cannot have an exponent greater than 1. That would be a nonlinear function. Also, there's certain things. You have to be able to write it in slope-intercept form. Cannot have an exponent greater than 1. As long as it passes those two things, it's linear. So to determine if any function is linear, we must remember that for a function to be linear, we must be able to write it in slope-intercept 1, and this is all the other things. Cannot be an exponent greater than 1. X and y variables cannot be multiplied by each other. Also, if there is any division involved, you cannot have the x on the bottom of the division. So we'll go through these as a class just to save time. Do we think this is linear? Yes or no?
Yes.
Yes. There's no exponent greater than 1. It's in slope-intercept form. That is linear. You can just write linear or nonlinear. You can always write in the rest of this later. Okay? All right. The next one. What do you think? Linear or nonlinear? Nonlinear, and here's why. Yes, that's a variable. Yes, that could be 1, but couldn't it also be 2?
Yeah.
Or 3 or 4? So because of the possibility that could be greater than 1, that makes this non-linear. The exponent could be greater than 1. You want to know where I got these? Directly from the state's FSA website. So a question like this should appear on your state test. I got their numbers directly from their stuff. Now what about this? Do you think this is linear?
No.
No, because of division and the x is on the bottom. If the x is on the top, it could be linear. It could be. But the x is on the bottom. Non-linear. What about this one?
Nope.
Nope. Why?
Because it has an exponent greater than 1.
Because it has an exponent greater than 1. Nonlinear exponent is 2. What about this one? Linear or nonlinear? It is linear. The y-intercept is 4, and then class, I want you to pause for a second and look up here. Looking at this equation, what is the slope for this?
1.
No?
1.
0. The slope is 0. Why is it 0?
Oh, y equals.
If I have one. So y equals 4. So we go to 1, 2, 3, 4. We put a dot. There's no slope here. Do you see an x? No. Which means that, let me ask you a question. If you say the slope is 1, wouldn't that change this? But if I say the slope is 0, anything times 0 is equal to 0. That would cancel, and a 0 slope wouldn't change it. So we would put a dot at y equals 4, and then it's just a horizontal line. Is that linear? Yes, it's a straight line. It's horizontal, but it is in fact linear. Okay, so linear can be written in y equals mx plus b form, where slope is 0. And then what about this last one? Would this be linear, yes or no? Yes, it would be. Here's why. Let's ask you a question. Do you see an exponent greater than 1?
No.
No. And couldn't I just move the 2x over to the other side?
Yeah.
Using inverse operations? I absolutely could. And this would become y equals negative 2x plus 4. You'll see this in more detail in the next module. Just know right now that because there's no exponent here, it doesn't break any of the rules. All you have to do is move that 2x over, it can be rewritten in y equals mx plus b form. What's up?
Why'd you change it to -2?
Well, here's what happens.
What you mean?
Let's look at this. Let's go to 2x plus y is equal to, what was it, 4?
Yeah.
4. So, if I draw my line, and I want to write this in slope-intercept form, I use an inverse operation. What's the opposite of a positive 2x? So if I subtract 2x from both sides, this cancels, and I get y is equal to -2x plus 4. Is that in slope-intercept form now? Yes, with a y-intercept of 4 and a slope of -2. Good. Remember, it's not -2x, it's just -2. Okay, so, looking at graphs real quick, let's just go. This should be easy for you guys. Let's go to Jiwa. Is this linear, yes or no?
Yes.
Yes. Straight line, that is linear. Pretty simple. Mr. Meza, top right. Is that linear, yes or no?
No.
This is linear. I didn't ask you if it's a function, I asked you if it's linear. Is this a linear function? These are all functions. We're looking for linear, straight line. So this is a function, but it is not linear. Non-linear. Okay. Mael, right here. Is this linear or non-linear? Non-linear, pretty straightforward. It's a function, but it is non-linear. Dante Jackson,
Yay.
the one to the right of that.
Okay.
Is that linear or non-linear?
Linear.
That's linear, we just dealt with that one. Y equals 4. So that is in fact linear. Okay. Thank you. Maria, linear or non-linear? Non-linear. Good job. And then Autumn Davis, last one, linear or non-linear?
Linear.
It is in fact linear. And if you look carefully, aren't these all the ones that we just did on the previous page?
Yeah.
Yes, they are. Right here, right here, right here, right here. It's all the same ones. It just shows you what they look like when they're graphed. Any questions on this? Yeah, what's up?
What happens if there's 2 straight lines, like an X?
If it's 2 straight lines like an X,
Yeah, like on the.
that'd be 2 different equations. They'd both be, if it was 2 straight lines, it'd be 2 separate linear functions. Right? Because it's 2 separate lines. If it was the same line, something like this, 1, 2, that's the only way you could make it. You couldn't make an X with one line. You couldn't. There's nothing that you can graph that would go up, come back, come all the way around and do that.
Of course.
If you
What
can
about-
find something like
what
that,
about
make
that
that your doctoral thesis.
What about the bottom left hand?
What happened? No, that goes like this.
Oh, cause I see.
Ah.
Ooh. You got it.
Okay. All right. Graphing functions. Shh. To graph linear functions, remember that inputs correspond to x values, outputs correspond to y values. When we run an input through the function machine and get an output, we created a coordinate pair that we can graph. We circled all the way back to the beginning, kiddos. This is exactly what we did in the beginning. We had an input. This is technically my little machine here. And I get an output, that becomes a coordinate pair. Once I get enough coordinate pairs, I can graph it. If you don't believe me, look. Way back when, a long time ago, that is where we started. Input, function machine, output. Now the only difference is we're going to take those points, we're going to throw them up on a graph to see what it looks like. So, I selected the inputs for you, and all we do is substitute these into the function, or the equation. This should be a function for x. So here, I put 0 in for x. -2 times 0 is 0. My output is 5. That gives me a coordinate pair. I go to the next one. I substitute in 1. 5, -2 times 1. 5 minus -2 is 3. That gives me the coordinate pair of 1, 3. I substitute in 2. Remember, order of operations. Multiplication comes before addition or subtraction. -2 times 2 gives me -4. 5 minus 4 is 1, and that gives me 2, 1. And then we put in 3, y equals 5, -2 times 3. What's -2 times 3? -6, what's 5 minus 6? -1. So that gives me 3, -1. I can take all these points and I can graph them. So 1, 2, 3, 4, 5. And then I graph all of these points. This graph is a straight line when I connect the dots, which means, is this function linear or nonlinear?
Linear.
This is a linear function. Good. So it's simple. You're taking inputs, putting them through the machine to get outputs. One more to go. One more. We have this?
Yep.
Okay, like I told you, still, this is a pretty generic function. The only thing you have to be careful here is order of operations. Now here, we start going back to our old friends, exponents. Exponents, you just have to remember the rules. So if I substitute in -2, it's -2 squared minus 2. So -2 squared is basically -2 times -2, which gives me what? Positive 4. Positive 4 minus 2 is 2. So I put in -2, I get out 2. That's -2, comma 2. That's my first coordinate pair. Then I just repeat the process. You have to be careful when you're doing this. That's the only place you can really make mistakes. -1 squared, 2 negatives, we multiply and make a positive. So 1 minus 2 gives me -1. That's -1, comma -1. And you just repeat the process. I substitute in 0. What is 0 squared? 0. Minus 2 gives me -2. So this is 0, comma, -2. I substitute in 1. What's 1 squared? 1. 1 squared minus 2 is -1. 1 squared is 1. 1 minus 2 is -1. So that gives me 1, comma, -1.
I didn't measure one twice.
Because, as you're going to see, this function is not going to be linear. How did I get -1 twice? Because when I square a number, it's always going to be positive. If I square a positive number, 2 positives make a positive. If I square a negative, 2 negatives make a positive. So really in both of these, I'm just subtracting 2 from 1, and I get -1 and -1. So when we graph this, let's go and graph this. 0, -2. And let's see, -2, comma 2, -2, comma 2, -1, comma -1, and this is what's known as a quadratic equation. So the graph of this is going to look like a parabola, which means it's going to
I love you, parabola.
go down and it's going to come back up like that. And then the question is here, is this a linear equation, yes or no? No, the graph is a curve, also known as a parabola. This is a non-linear function. Any questions? Robin? Any questions?
It's 50.
Okay.